It's beginning to happen. For the past 2 years, I've speculated about what artificial intelligence will do to science, and we can now see it happening. AI's taking off. Is AI destroying science or saving it? Is this the beginning of the singularity? Or is it just another year in which I'll regret my words? Let's have a look at what's going on. It's undeniable that AI has been advancing rapidly in the past year, and the rumor mills are very, very hot. The most recent rumors were ignited by OpenAI hiring a head of preparedness to ensure the safety of running systems that can self-improve. That sounds serious. NVIDIA CEO Jensen Huang recently said that intelligence is about to become a commodity. I think he's right, and most scientists who basically make a living from their intelligence haven't yet really grasped what this'll mean. An increasing number of mathematicians and physicists now actively use large language models for proofs and brainstorming and references and calculations. Some mathematicians, including the Fields Medal winner Terence Tao, have fully embraced this, using AI to find new and better proofs. But AI isn't just being used in the paper writing. In a recent survey by Frontiers, 53% of peer reviewers now admit to using AI tools in some part of the review process. We don't have numbers for it, but it's a safe bet that they also use AI to write and rate grant proposals. No one has any idea what the consequences will be, except for one. More papers will be written. In a new study that just appeared, the authors found that researchers who adopt large language models become stunningly more productive. Using AI increased paper output on average by 40% for non-native English speakers, as much as 80%. And this was data only until the end of 2024, when they used it mostly for writing. Now extrapolate this to the next year. It'll be crazy. You see, in scientific publishing, productivity is the most important variable. Once researchers see that frontier models help them produce more papers, the adoption rate will go to near 100% across pretty much all scientific disciplines. And we don't have people to review all these papers. Another most interesting development is that some universities like MIT and the University of Oxford have gotten ChatGPT Pro subscriptions for their entire staff. That comes through an OpenAI program called NextGen AI, which currently includes 15 of the world's top universities.
OpenAI is investing $50 million to give universities free access to cutting-edge AI.
Also a good example for how AI is likely to increase differences, I'm afraid, rather than easing them out. But look at the big picture. 2 years ago, you'd have laughed at the thought that GPT would aid anyone in research other than through text, and that isn't even yet AGI. I've been telling you previously about several AI scientist startups that have sprung up around the existing frontier models. Usually they combine the large language models with some symbolic solver or similar iterations fine-tuned for specific purposes. These have now popped up everywhere. And of course, the big companies themselves are in on it too, like Anthropic, for example, that's put out Claude for life sciences. Taken together, I have a feeling that in 3 years, scientific research as we know it will no longer exist, because scientists will replace the work that was previously done by students and postdocs with AI at a fraction of the cost and time. This will start in the areas that most rely on coding and mathematics, which is why theoretical physics is one of the major aims of AI science startups. Within 10 years, theoretical physics will basically be over. I mean, it'll be over for humans. We just won't need them anymore. Want some theoretical physics done? Just buy a few days of compute on this new model. The US government has fully leaned into this by launching the Genesis mission in late 2025. In their own words, it's a dedicated, coordinated national effort to unleash a new age of AI-accelerated innovation and discovery that can solve the most challenging problems of this century. It tasks the Department of Energy's 17 national labs to build an integrated AI-driven discovery discovery platform in partnership with industry and academia. As part of this mission, Google DeepMind agreed to provide the DOE scientists early access to its frontier AI tools. It's a smart move. As I've said before, AI is not a wait-and-see technology. Who has a head start in this area will basically be impossible to catch up to in 1 or 2 years. If we in Europe miss this boat, we're finished. Each time I make a video about this, there are some people in the comments saying it's all hype, this excitement is going to go away, machines will never be able to be creative or to really think and so on. I hear you, but I think you're dead wrong. This is really happening. And Jensen Huang's comment that intelligence will become a commodity, something that you buy as much of as you need, is spot on. I really think that humans could also need a head of preparedness. Tracking technology has become shockingly advanced. I don't mean that whenever you buy socks, you have to endure socks ads for the next 2 weeks, though there's that. Neither do I mean CCTV, that's been around for decades. I mean all the ways that companies keep track of our location using Wi-Fi, Bluetooth, and Face ID. They now also use LiDAR and radar, and there are several new technologies which will make tracking people even easier. I don't know how else to describe this as the end of privacy. Let's have a look. Earlier this year, a group of researchers from Italy showed that they can identify people by analyzing merely how their bodies alter the Wi-Fi signal in a room. You don't need cameras for this. All you need is a Wi-Fi and a way to measure the signal, and then you throw deep learning at the data. Your router knows more about you than your husband. This works even better, of course, if you have a portable signal like a radar. Radar used to only work for big objects, but now there are handheld devices that can identify objects and people through walls. This has become possible by using a large bandwidth, that is signals of different frequencies, and then using artificial intelligence on the signal. These radar systems have been used, for example, to find people buried under rubble after an earthquake, but certainly there are other things you can do with them. Another technique is to reconstruct sound from visuals. The idea is that one uses a high-speed camera to track oscillations of objects and uses this to compute sound waves. This was first proposed by a group from MIT about 10 years ago, but this year several Chinese groups have demonstrated how this can be done much more efficiently and also much cheaper. You can listen to what people say looking at empty bags and leaves. And just a few weeks ago, physicists have shown that if you bounce a laser off a surface like a mirror or window, you can use the reflection to reconstruct the sound. Basically, they're writing papers about how to better spy on others. Other research groups have developed ways to look around corners or behind objects by reconstructing reflections on surfaces. This idea too has been around for about a decade, but used to require laser light and suitably shiny objects. Now they can do it with standard optical cameras using everyday objects like door handles or marks from dozens of meters away. And it's no longer just stills. They can now reconstruct video in real time. These technologies are still under development, but everyday surveillance has become standard, especially in the United States and China, and it's becoming more common also in Europe. Walmart, for example, collects data about shoppers with multiple technologies. They have cameras, of course, and they tag products, but in addition, they use a combination of your phone's Wi-Fi and Bluetooth, the signal, to identify and keep track of your position, whether or not you log on to their Wi-Fi. We know this because it's in their privacy policy. Some retailers in the US, such as Albertsons, have admitted to using face identification on video recordings. It's being rolled out in some stores in the UK too, and is already commonplace in China. Walmart denies they use Face ID, but we have this recent incident of a man who bought something at Walmart, paid with cash, didn't have a phone with him, and was later asked to rate the item. So, well, I guess that was magic. A similar accusation has previously been raised against Home Depot. It's not just individual stores. Many malls also use a combination of cameras, Bluetooth, and Wi-Fi to track customers. Melbourne University tracked student protesters using CCTV and phone signals. The London Underground has been tracking people's motion from their Wi-Fi signal for years. Since last year, the New York Metro also uses video recordings to analyze passenger flow, or so they say. Manchester Airport now uses LiDAR to track passengers. Dallas Airport plans to do this too. The companies using these devices say they're better than cameras because you can't use LiDAR or radar to identify people from their faces. But make no mistake, all you need to do is cross-check one person once with them, say, scanning a boarding pass or making a purchase, and you have all their steps on record. It's not just indoors either, because the 5th generation of mobile networks, 5G, can locate devices within about 1 meter. This means that in any building or street equipped with such a system, every phone connected to the network can be located with high accuracy. People tracking is most advanced in China, where at this point you basically can't go anywhere without the government's knowledge. They have a nationwide system that keeps an eye on where you go and what you do, and they aren't even shy of admitting it. In Europe, privacy laws dampen companies' enthusiasm to do this kind of thing, so there's some attempt at keeping tracking anonymous, but the thing is that once you just have enough data, you can identify people uniquely. I think that this trend is impossible to stop. It's just where the world is going. We're collecting data about everything, everywhere, all the time, and with that, privacy will end. It's not going to happen one day to the next, but slowly and creepingly. It'll change society dramatically. Privacy used to mean closing the curtains. Then it meant clearing your browser history. Now it means leaving your phone in the fridge, and even that's only a temporary solution. On the bright side, we'll never again have to remember a password. They'll know it's you already. Physicists don't know what most of the matter in the universe is made of. They think it's some sort of dark matter that makes itself noticeable only through its gravitational pull. But that may just have been totally wrong. Today I want to talk about a new idea that explains our observations without introducing any new type of matter. It's rather that we might have misunderstood how gravity really works. It's a new type of modified gravity, one that could overcome the problems with early ideas and maybe even connect the observations to quantum gravity. Let's have a look. The laws of physics that we have discovered have one thing in common: they are local. This means that objects in two different locations can't interact with each other. They don't know anything about each other. A bit like theorists and experimentalists. It's only by sending some sort of signal from one object to the other that they can react to each other's presence. We have no idea why the laws of nature are this way. There's no particular reason why they should be. It's just that it corresponds to our experience. Newtonian gravity is not local. This bothered Newton a lot back then. You see, if you take Newton's law of gravity with the gravitational force proportional to the mass divided by the square of the distance, then if you move the mass, the distance increases and the force changes instantaneously everywhere. Newton was greatly bothered by this. He called it action at a distance, and that's also what Einstein meant by the phrase. Einstein's theory of general relativity, which we use now to describe gravity, doesn't have this problem. In Einstein's theory, gravity is described by the curvature of space and time, and that curvature is caused by the mass and energy in the space-time. If you move the mass that causes space-time to curve, then the curvature changes, but not instantaneously everywhere. The change spreads outward at the speed of light, so Einstein's theory is local, as physicists say. The problem is, astrophysicists have for decades piled up evidence that something's badly wrong with our understanding of the universe. Because when we look out in the cosmos at our own galaxy or other galaxies or clusters of galaxies, then the predictions of Einstein's theory just don't come out correctly. Space is curved much more than it should be, given the mass and energy that we think is there. The common way to fix this is to postulate this stuff, dark matter, which physicists have tried to find for decades. It's become somewhat of an embarrassment, really. The authors of this new paper now propose something else entirely. They say that maybe gravity is not local after all. You see, because then the curvature in one place is not just caused by the masses in that place. On top of that come contributions from masses elsewhere. And how does that look? Well, it looks like there is too much mass in space-time. The idea that dark matter is really just an artifact of non-locality isn't entirely new. What's new is that just the other week a new paper appeared whose authors argue that non-local gravity can explain pretty much all the observations normally attributed to dark matter. They do this not by going through all these observations, but rather they show that in some regimes at very large distances such as galaxy clusters, the non-local gravity looks just like dark matter. However, within galaxies, it behaves differently, and it appears much like modified Newtonian dynamics, MOND for short. MOND, if you remember, was the major competitor of dark matter. It works nicely in some cases, like for galactic rotation curves, but it's got problems with other things like galaxy clusters. Basically, the observations have told us for at least 20 years that what we really need is a theory that interpolates between something like dark matter on the scale of clusters where MOND doesn't properly work and something like MOND on the scale of galaxies where dark matter doesn't properly work, and this non-local gravity just seems to do it. Better still, the idea that gravity isn't entirely local is something that you would expect to naturally occur in a theory of quantum gravity, because we know that quantum theory isn't local. I really like the idea, but, oh yes, there is a but. The but is that the theory which they proposed has very complicated differential equations that I strongly doubt can be made compatible with any quantum theory. They are also, on a more pragmatic level, just incredibly difficult, and that'll make it hard to find widespread acceptance. Also, the transition from MOND to the dark matter regime doesn't come out of their formalism naturally. They basically put it in by hand. It's the kind of math that makes even grown physicists cry into their coffee. So I give this paper a 5 out of 10 on the bullshit meter. It hasn't yet been peer-reviewed, but it's probably mathematically correct, by which I mean I didn't check the calculation, but they sound like they know what they're doing, which, if nothing else, tells you that you shouldn't trust theoretical physicists for financial advice. However, the theory has clearly been designed to make this interpolation. This is not a problem. I mean, this is how theories work. You make assumptions and then you see how they fit the data. But then again, we could just as well say, well, we use dark matter in some regimes and MOND in others and not bother with all this non-local stuff. Personally, I think dark matter is cheese. It just makes everything a little more attractive. But if it's really non-local gravity, then this means, well, everything in the universe is connected, including, eventually, theoretical physicists and reality. Physicists have dreamed for a long time of a final theory, one simple set of equations that explains everything, all forces, all particles, no loose ends. Today I have a new paper that explains why that dream is unlikely to ever come true. It's because simplicity is in conflict with the presence of life in our universe. I find this a most interesting twist. Let's have a look. Physicists have discovered 4 different interactions which are the basis of everything. That's the electromagnetic interaction, the strong and weak nuclear interactions, and gravity. Everything else follows from that. But these different interactions don't seem to have a common origin. They're lacking a unification. Physicists speak of a unification if the electromagnetic strong and weak interactions have a common origin and a theory of everything, if gravity too can be explained from some to-be-found underlying structure. String theory has been a hot contender for a theory of everything, hot enough to evaporate every grant in its vicinity. However, neither string theory nor any of the other approaches that physicists have tried has explained just why the interactions in our universe are what they are. And because string theorists couldn't explain that, they postulated that all possible interactions exist, each in its own universe. Then the idea is there is nothing to explain. Our universe exists because any possible universe exists. I've always found the multiverse a quite appealing idea. I find it somewhat depressing that this universe should be the only one there is. But of course the question is, well, what does it matter that all these other universes exist if we can't ever observe them? And what's the point of saying that the existence of all these other universes explains why ours exists if we can't actually calculate anything from that? Well, physicists have said if we knew all the possible ways that universes could be, then we can at least calculate the probability that the laws of nature are one way or another. However, if we do this, we have to take into account our observer bias. We can't observe any laws of nature that don't allow for life to arise. Now, this is where the new paper comes in. The author asks what the presence of life in our universe tells us about the properties of the fundamental interactions. Concretely, he looks at how different physical parameters can vary across universes and how that affects things like star formation, nuclear reactions, and the stability of matter. He then asks which kinds of underlying theories make a universe like ours likely and which make it extremely rare. The surprising result is that the idea that the fundamental forces are unified does badly. Well, at least I found that surprising, but the more I thought about it, the more sense it made. You see, a unified theory will, in one way or another, tie different parameters to each other. Then, if you vary one parameter, you break several other relations at the same time. As a consequence, the more strongly different interactions are tied together, the more difficult it becomes to create life. Most universes end up either short-lived, empty, or chemically boring. More flexible theories do better. Theories where parameters can vary more independently produce a larger fraction of observer-friendly universes. In other words, once you include the multiverse and selection effects, physics that is slightly messy beats physics that's mathematically elegant. The paper goes further and shows that this is not a tiny effect you can ignore. Under reasonable assumptions, whole classes of unifying theories become extremely unlikely once you assume that life must exist. It means that in a multiverse, you wouldn't expect to find yourself in a universe governed by a unified theory. There are, of course, caveats. This kind of argument depends on assumptions about how parameters vary and what conditions are necessary for complex structures to form. Change those assumptions and the details can change, but the core tension doesn't go away. Unification reduces the freedom of parameters. Life requires a fine balance that's easier to achieve with more freedom in the parameters. These two ideas pull into opposite directions. I think this is an interesting result whether you like the multiverse or not. You can be skeptical about the multiverse and still learn something here. The deeper message is that if you want to create complexity, then overly simple laws of nature might just not work. Maybe that shouldn't be so surprising. After all, the laws of nature would be much simpler if there were no particles or interactions at all and the universe was just empty. That's a very neat and elegant unified theory, but it would make a terrible YouTube channel. I give this paper a 5 out of 10 on the bullshit meter. It's a nice argument, but then again, the multiverse might just not exist. In summary, depending on how you look at it, this paper tells you one of two things. Either the multiverse has just killed our dreams of a final theory, or life is bad news for unifying physics. So maybe the final theory doesn't exist, which means physicists can keep on publishing forever. The only thing truly unified is our confusion. Thanks for watching. See you tomorrow.